Good day everyone. Today I'm going to give you a video tutorial of solutions from Advanced Engineering Mathematics 5th edition textbook, and was prepared by me. My name is Ryan M. Hallelujah. Now here are the solutions for problems number 60 of page 107 and number 70 of page 108. Now, first problem states that using variation of parameters show that if R1 is not equal to R2, the coefficient A can always be determined so that y is equal to ax e to the power of R1x is a solution of the equation y double prime minus quantity R1 plus R2 y prime plus R1 times R2 y is equal to a e to the power of R1 x. Now the solution. First, you have to find the roots to find the complementary solutions, and you have to set the equation into a homogeneous equation. Thus, we have an auxiliary equation, and we let m to denote for roots, and we have this equation m squared minus quantity R1 plus R2 m plus R1 times R2 is equal to 0. Using the quadratic formula and then substitute values, we have this m is equal to that equation. And then with further ado and further simplifications and computations, we have the values for m, and m1 is equal to R1, m2 is equal to R2. Okay. And second, we have to determine what type of damping, and there are three cases. Since we have two distinct real roots, therefore this is case 1 overdamp case, and we have this as our complementary solution. Y is equal to c1 e to the power of R1x plus c2 e to the power of R2x. And third, we have to use the variation of parameters, and to find the particular solutions, we use this formula y is equal to u1 times y1 plus u2 times y2. Thus, by Wronskian's technique, to find u1 prime, we have this equation, which is 0, and a to the e to the power of R1x is our function in a non-homogeneous equation. And then we have e to the power of R2x, that is our y2, and the first derivative of y2, which is y r2 e to the power of R2x, and over e to the power of R1x, that is our y1, and R1 e to the power of R1x is our y1 prime, and so on. And then to solve that, solving that, we can get this answer that u1 prime is equal to negative a over R2 minus R1. And then we integrate u1 prime to get u1, and we have that equation. Thus, u1 times y1 is equal to a over R1 minus R2 x e to the power of R1x, which is one of the particular solution. However, y is equal to ax e to the power of R1x is a solution of the equation. Therefore, we have a over R1 minus R2 is equal to a. Simplifying, we have a is equal to a R1 minus a R2. Now, we know that y is equal to a x e to the power of R1x is equal to a over R1 minus R2 x e to the power of R1x is a particular solution. So it is wise to say that coefficient a should not be equal to 0. Else we have, when a is equal to 0, small a is equal to 0. And substituting the value, we can get R1 is equal to R2, which is a contradiction to our assumption. Therefore, by proof of contradiction, we can say that y is equal to ax e to the power of r1x is equal to a over r1 minus r2x e to the power of r1x is said to be a solution of the equation y double prime minus quantity r1 plus r2 y prime plus r1 r2 y is equal to a e to the power of r1x for all a except 0 and r1 is not equal to r2. And next problem is using the method of variation of parameters, find a particular integral of the equation y double prime plus y is equal to x to the power of 1/2. And we have this solution. Okay, then again we have to find the roots to find the complementary solutions, and we set the equation into a homogeneous equation. So we have y double prime plus y is equal to 0. Thus we have an auxiliary equation m squared plus 1 is equal to 0. Using the quadratic formula and substituting the values, we have m is equal to plus and minus I. Second, determine what type of damping. Since we have conjugate complex roots, therefore this is case number 3, underdamped case, which is our complementary solution is y is equal to c1 cosine of x plus c2 sine of x. Third, use variation of parameters, and that is our equation for the particular solution. And using Wronskian's technique, u1 prime is equal to negative x to the power of 1/2 sine of x, and we integrate u1, and then we have u1 times y1 is equal to negative cosine x integral of x to the 1/2 sine x dx. Okay, that is one of the particular solution, or the particular integral u1 times y1. And to find u2 times y2, which is another particular integral of the equation, and that is by superposition theorem. So we have u2 prime is equal to x to the power of 1/2 cosine of x, and u2 y2 is equal to sine x integral of x to the 1/2 cosine x dx. Okay, and that's all. Thank you.